So the work that I'm going to talk about today, partly stuff that I've been doing, but partly, or lots of the work that people like Claire and Mitchell have been doing in their PhDs as part of the Source to Spectrum project. And Claire's going to be talking a lot more about this next week as a plug for Claire's talk in the ISCG workshop. And we've been through that. So everyone's pretty familiar with the Hildebert GRV event on the Gawler Craton. And we know there's a wide range of mineral deposits associated with it. Obviously, ISCGs, we have Weed Nana as an example where we've got magnetite and gold, but no copper, for example. We've got silver in Paris, just below the GRV, and I don't have a laser pointer, sorry. And then we have what people have traditionally called the Central Gawler Gold Province. At the moment, the only thing that I'm confident is Hildebert age is Tarcoola, and the other deposits that we've been working on, it's becoming less and less clear exactly what age they are. So I'm not going to touch too much on that today, but stay tuned for that. And also, as people have been saying the last few months, it's worthwhile highlighting that probably the ISCG versus gold deposit provinces are kind of an artificial construct, and they're really just what we see on either side of the GRV. And as I'll talk about, lots of the kind of factors involved in mineralisation potentially actually seem to be shared between both provinces. So I come from a igneous geochem background, which means I'm biased towards that side of things. I think probably the most efficient way to move metals from the mantle and lower crust to the upper crust, where they can form a deposit, is actually in a magma. There's obviously plenty of deposits that don't form this way, but for what we're talking about, I think that's probably relatively important. And if we take the porphyry copper system as an example, then it's not necessarily the source that's super important. It doesn't necessarily need to be particularly enriched in copper or gold, for example, but it's actually how that magma evolves as it goes from the mantle to the upper crust. So people have suggested that there could be some enrichment of copper and gold in the lower crust as you keep bringing those magmas in before they finally get remobilised. But people largely say we need to have an oxidised magma to stop sulphides precipitating out as we're crystallising this thing in the lower crust and mid-crust. And it's also useful to have wet magmas because that stops magnetite from crystallising out early, which leads to sulphide saturation as well. So really what we're trying to do is keep the metals in the magmas for as long as we can. Or if we drop them out, then remobilise them later on. So some of the factors that people have talked about, water, oxidation state of the magmas, early or late sulphide saturation, the iron content makes a difference, particularly for sulphide saturation, whether it's periluminous or not. So that can play some weird tricks. So gold doesn't like periluminous magmas, but silver isn't affected by them as much. And then things like fluorine and chlorine mobilise metals, but also change how the magmas behave. So in the Gawler, we know that there's differences in the types of magma between the ISCG province and the rest of the Gawler, but we don't necessarily know whether those factors such as oxidation state and things like that are systematically changing as well with the I-type stuff that Anthony Bard and people at Survey have worked on over the years. So at the moment this is kind of a progress talk because we're starting to bring together a whole series of different observations into looking at which of those factors we see across the craton and which ones potentially are important for some deposits but not important for others. So I'm going to actually start by jumping in at Paris, partly because I've got some new ages on it, which is nice, and also it's a really nice example on how we see differentiation within the suites. So hopefully most people will know, Paris is a silver deposit, currently held by Investigator, 42 million ounces, it's got some lead there as well. And this is hosted in an alteration brecciation system with 2 volcanic phases that Investigator have identified. And if we look at the ages that we now have for these, so these are precise TIMS ages. The one on the left is about 2 weeks old, so it's something I got when I was in the US. So we've got two ages. We can see there's about 3 or 4 million years worth of magmatism in the Paris system. What's really nice is if we compare that to Olympic Dam, then we can see those times match up really, really quite well with the timelines we see at Olympic Dam. So the older system, the older volcanics, 1594, going through to the younger volcanics at 1591. So that's things that are two magmatic systems that are nominally in the IOCG versus the central Gawler province that have the same timelines. So what's really interesting, and this work comes from Scott Haley originally, and then the investigator team have done a lot more on this. And I've just grabbed a little bit of data from them. The volcanics at Paris have really quite unique zirconium and hafnium ratios. So this is a measure of how fractionated a magma is. And the reason why Scott Haley was excited about it, and John and Jason and people at Investigator, is that these things are quite often associated with mineral deposits. So the reason that is, or the reason why this is interesting, is zirconium and hafnium are both +4 cations that behave almost exactly the same in most settings in the crust. When you go from a mafic to a felsic magma, you can change that ratio a little bit if you've got a I-type, calcic, titanium-rich magma that crystallises out titanite, amphibole and CPX. A bit of water helps there too. The real thing that happens though is when you start crystallising out zircon. So that takes out zirconium and takes out quite a lot of hafnium too, but just not quite as much. So you drop that ratio down. So the St. Peter suite is an arc-related suite on the Gawler, arguably the only one in the Proterozoic. And it behaves pretty much like a normal magmatic suite. When we look at the Hildebrand suite, we can see straight away on the bottom right that we drop down to the values below 20. So you want down into the 18 in particular and 15 range. So this is when we get into really, really quite fractionated magmatic suites. A few of these data points are apolites, so we can ignore them, but actually the majority are what we call normal granites. So what's quite interesting about this is if we look at that bottom end and look at all of the data from the Hildebrand, so this is about 700 data points in the whole data set. Not all of them have all of the elements. We can see Paris in the blue dots. I don't know why I'm pointing the clicker at it, but we can see Paris in the light blue. And then if we look at the really fractionated magmas, they're actually all in central Gawler, so in the Wilgina and Neutz domains, which are the old domain names, but basically running along the edge of the GRV. The IOCG granites, so the eastern Gawler granites on the other hand, don't go that far down. So that means there's a fundamental difference between those two. And I actually haven't quite worked out why this is occurring yet. They have similar zirconium abundances. Interestingly, the central Gawler province does appear to have higher fluorine contents in our data set. And that's the opposite of what people would potentially expect, given the so-called A-type granites in the IOCG province. But that actually may be playing a role here. What's really nice is that fractionated granites are associated with mineral deposits. This is a diagram that combines zirconium and hafnium with niobium and tantalum. And generally when people start looking at this, they start talking about tin tungsten granites, lithium, tantalum, things like that. I don't think that's particularly relevant for the Hildebrand suite, except for the two little blue dots down the bottom. They're clearly going to be the next lithium deposit in the Gawler Craton, which I'm sure everyone will be excited about. I can't actually even remember where they're from, so I can't even give you that answer. What we mainly see though is that the Hildebrand granites avoid those tin tungsten kind of fields. The reason for that is that these magmas are not as periluminous as the true tin tungsten style granites. So although they end up periluminous, they're not fractionally crystallising out biotite as a major phase early on. So that pushes them to the right straight away. And then once we get down to the bottom, where we start to looking at the niobium tantalum more, we're also not seeing, we're seeing a bigger control, probably from oxides. So because these magmas aren't particularly reduced, then we start pulling out tantalum as we start crystallising them. So that's not great for forming a tantalum deposit, for example, because it means that you're dropping out the critical metals early on. It does highlight, though, that some of these magmas do get down to those really hydrated and fractionated phases, and does raise the possibility that we can start seeing potentially quite fractionated style deposits. So I put in an assumption there that we're dealing with oxidised magmas. Everyone looks at the Hildebrand suite and thinks it's oxidised because it's red. That's actually basically a subsolidus phenomena, so it doesn't tell us much about how the granites have evolved. So what we actually need to do to understand that is to look at the whole fractional crystallisation path, because that's what we're interested in. To some extent, we don't care what happens right at the end, unless you want a mineral deposit. But if we look through, we can start seeing whether they're reduced or oxidised. So we have in the green dots, the dark, kind of badly coloured green dots, we have some northern Gawler granites from the Hildebrand suite on gabbros. And they follow what we consider to be a reduced path in magnesium number space. So I'm slightly bastardising magnesium number, but it actually works relatively well for reduced and oxidised in this sense. If we look at the ICG province, the central Gawler granites, they all actually follow an oxidised trend, which is really nice. It obviously helps to keep metals in the magmas. But it also means that fundamentally from very early on, these things are kind of behaving similarly. So despite the fact we've got a really old enriched mantle, or subcontinental lithospheric mantle, that could have been enriched even going back as far as the Archean, and we see variations in that, which Claire has talked about in her PhD, we actually still see roughly similar controls. So we've still got oxidised magmas coming up. And you can see that these magmas on the right-hand side actually hold on to their copper a little better as well, which is good. It's what we'd expect to see. If they're not reduced, they're not going to drop out sulphide straight away. So we should be able to keep some of that copper in the system. Still goes down, but that's kind of not a problem. That's to be expected. So it's nice that we can see similar oxidised states for the central and eastern Gawler, but we actually do see differences between those suites. So this is work that Claire's currently been doing, so some of these are a couple of weeks old as well. And we've got trace element compositions of zircon compared to the porphyry system, and we can see that in blue, the ICG province granites actually do have distinct compositions to the general granites in the region. All of them are quite oxidised still, which we see from the cerium anomaly. But we actually see, again, that there's more fractionation occurring in the general Gawler granites. So none of these really plot in the porphyry fertile field, but that's not surprising because these granites are dry granites. We wouldn't expect them to have really high europium numbers, so that kind of makes sense. What it is nice is that it shows that there's trends across them, and we're actually still kind of working out exactly what this means. Everybody would say that the A-type granites are more fractionated and drier, but this data suggests that's not actually the case. So we're kind of working through now what exactly is going on in that sense. So takeaway messages from this are, in terms of looking for metals staying in magmas, the central Gawler Craton actually behaves pretty similarly to the ICG belt in terms of being oxidised magmas. One of the differences is that it pushes to really quite highly fractionated values. So that does potentially open up more of the critical metals or rare metal type behaviours where you get things that have stayed in the magma coming out really, really late in a really hydrous pegmatitic style phase. And potentially that does relate to things like Paris. We have similar early behaviour of metals. So the lower crust seems to be behaving relatively similarly, which is quite nice. What the big question is at the moment is what is the water and sulphur content of the magmas? So the hygrometers we're using for the suites are relatively insensitive. So we can say they're all dry, but we can't say, you know, if one's drier than the other and what effect that will have on things like magnetite precipitating out. And although there's talk of ICGs being the sulphur poor variety of porphyry copper deposits, we're actually seeing fundamental differences in the granite types as well. So we wouldn't expect them to behave the same. So we don't actually know whether the sulphur content is coming out early, and that's why they appear to have lower sulphur, or whether we're just actually having a completely different evolution path that's controlling the apparent sulphur or pore nature of these deposits. And that's it.